Okay, let's get started. Welcome. The first speaker is Professor Ofer Zeitouni from the Weizmann Institute, who'll tell us about characteristic polynomials of random matrices, log-related fields, and universality via dynamics. Ofer, please.
Thank you. Thanks for the invitation, and I'm really sorry that I couldn't be there. I wish there will be another occasion in the future. So I'm going to tell you about some results about characteristic polynomials of random matrices. So let me, without too much of in terms of introduction, let me give you a little bit of background, and then I will state some results. The background connects to the what is now called the Fyodorov-Hyry-Keating program, and it can be stated as follows. Suppose that UN is a hard distributed matrix, random unitary. Then it has a joint law of eigenvalues by Weil's formula, which is written here with beta equal 2. So think of lambda I as points on the unit circle. In the complex plane, we have that as a joint density of eigenvalues. And we will allow more general betas, both because we can, but also because of some of the extensions will be particularly significant also for beta equal 1. And now you can ask all sorts of questions about this configuration of eigenvalues. Note that if you write it in the language of statistical physics, namely you write this product as e to the beta sum of log of lambda I minus lambda j, what you obtain is, for I less than j, what you obtain is a logarithmic interaction between point charges, and this is kind of a Coulomb gas interpretation. So this ties up directly with the notion of Coulomb gases of particles. So even if you don't care at all about random matrices, but you do care about systems of particles, this is what you have here. And you can ask all sorts of questions. I will focus on the following. Suppose we take, just some notions. We have a quantity, which is this one. So that's a random measure called the empirical measure of eigenvalues. And it is not a hard exercise to convince yourself from that formula that it just converges to a uniform measure on the unit circle. That's kind of obvious also from the rotation invariance of the unitary law. And what you could ask is for what is called linear statistics, linear because it's a linear functional of the empirical measure, which is written in this random variable zf that I wrote here. So it's sum of f of lambda I minus the expectation of this sum. In particular, if you take f on the unit circle whose average is 0, or in other words, is 0, so your coefficients is 0, then you ask about the fluctuations of these random variables. Now, if beta equals 0, which means that the lambda i's are just independent random variables, we all know that this should have scaling of square root n. That's the standard central limit theorem for independent random variables. But here, this is not the case. And in fact, it's a consequence. There are many ways of seeing it, but in particular, to make contact with some other areas of math, the strong Sego theorem tells you that you can write this the expectation or the integral against the density, the Laplace transform of this ZF against the density as a certain determinant, and the asymptotics of that determinant is given by this formula. So if you took from the beginning, recall that this expectation is just equal to this quantity, so this and that kind of match, and what remains is something of order 1. So it's this quantity sigma f squared, which is the h1/2 norm of f evaluated in the Fourier domain. So in particular, this tells you that this random variable is behaving like a Gaussian with this variance. Here, that I forgot to write. Okay, so much more than that is known. In particular, Johansson proved in a seminal paper about 25 years ago, he gave very sharp rate of convergence for this fact, and in particular, it applies to many more models, etc. But I'm not going to discuss it right now. Okay, so all that is well and nice, but what we would like to do today is to talk about the characteristic polynomial of such matrices. So this is a characteristic polynomial, or more precisely, the real part of the characteristic polynomial. And if you think about it, because the determinant is a product of functions of individual random variables, this corresponds in the previous language to the test function, to the linear statistic f, which is log of e to the I theta minus x. And if you compute the Fourier coefficients of this function, they are of order 1 over k. And in particular, this tells you that the quantity sigma f squared that was written here is going to behave like the sum of 1 over k, namely, it's going to converge to infinity as you sum to infinity. Now, this fact can also be written in a slightly more formal way by expanding the log determinant in a power series. So you can rewrite the log determinant. I see there is a delay. I will try not to move my screen so much. So the log determinant can be formally written as this power series. Of course, it's not a convergent power series, but let's disregard that for a second. It is a convergence power series for Z strictly inside the unit disk. And then you obtain this sum with random variables, which are the traces of un to the power k. And at least for beta equal 2, it was an important theorem of Diaconis and Shashahani, again, about 20 years ago, who proved that these traces converge to standard normal random variable with variance k, complex normal random variable with variance k, and independent. And so here again, you see that formally, this log determinant then becomes asymptotically a logarithmically correlated field, because it behaves like the sum from 1 to infinity of some IID random variable divided by square root k times z to the k. Okay? And to a large extent, what I'm talking about today is how to make precise all these formal calculations and what kind of consequences can you achieve from them. So maybe a first step was obtained by Keating and Snaith, who showed, and also by Weyand, who showed that this log normalized by square root log n. So before I proceed, you see for n fixed, of course, we know by Cayley-Hamilton that un of k are really variables that can be considered somewhat independent only for k, which is smaller than n. So it's natural to truncate this sum at k equal capital N, in which case the variance you obtain is of order log n. And so the result that I was just beginning to state of Keating and Snaith and of Weyand showed that indeed this is the right behavior when you look at it pointwise. Namely, if you take a fixed z and you look at the log of xn of z divided by square root log n, this converges to a standard Gaussian random variable, which is in complete agreement with the formal computation I did before. And slightly later, Keating and O'Connell proved that in fact, this sequence of random variable log xn of z behave like a log correlated field in the sense that if you integrate them, if you form the integral of log of xn of z times f of z, or g of z, integral over the unit circle where g is some nice smooth function, this integral becomes a Gaussian random variable whose variance can be written as a double integral of g against the potential log of x minus 1. So this all fits very nice together. And the point where I want to take this talk is to say, well, there has been a lot of work in recent years about log correlated fields and their extremes. In particular, in the Gaussian case, we kind of understand precisely how does a maximum look like. And before I tell you the results, I would like to field, the maximum has the same distribution as the minimum because Gaussian log correlated field, the law of the field and of minus the fields are the same. So the maximum and the minimum have the same behavior. However, for the log of xn of z, the minimum is minus infinity because at any eigenvalue, xn of z is 0. So this means that we cannot hope to transfer results in an automatic way, because if we did, we would get nonsense. And luckily, I'm not going to care about the minimum, so this is just a word of caution. I'm going only to look at maximum. And now you can ask, okay, maybe for the maximum, things work nicely. Before I state some results, I want to say also that there is an interest both to look at the real part, which is what I have kind of talked until now, but also on the imaginary part of the log. So if you think of the log as a sum of log of z minus lambda I, you can easily extend it and make sense of the log by taking a cut of the log on the negative real line. And so this is then very closely related to the eigenvalue counting function. So in fact, the imaginary part of the log at z minus the imaginary part, minus log of the imaginary part at 0, the imaginary part of the log of xn of 0, this difference exactly counts how many eigenvalues there are in the interval 0z. So if you care about that, understanding the fluctuations of the imaginary part tell you something about the fluctuations of counting functions of eigenvalues. Okay, and now I said it's a And the conjecture is the following. If I take the log of the characteristic polynomial and I look at the maximum, the answer turns out to be what you expect for Gaussian fields, almost, in the following sense. The leading order is of order log n. There is a correction which is of order 3/4 log n. And then there is a random variable. And this random variable converges in distribution to a particular random variable in the case of beta equal 2, which is the case in which the conjecture was made. This is just the sum of two independent random variable of Gumbel type. A random variable is called Gumbel if it has this as distribution, this function here as distribution, and this xn converges in distribution. So that's a conjecture. And in fact, this is one side of the conjecture, because the main goal was to tie between random matrices and the Riemann zeta function. I'm not going to discuss at all this link, but let me just say that the analog of that for the Riemann zeta function is the following. You look at the critical axis, you look at a random interval of size 1 taken uniformly high in the, let's say, uniformly between capital T and 2 capital T, where T is large. And you look at the maximum of the Riemann zeta function on that interval. They conjecture that the answer is very similar, except that one of these Gumbels is replaced by something else. Okay, so for the Riemann zeta function, you would have a very similar result, but it will not be a sum of two Gumbels, it's Gumbel plus something. One can state a generalization of this conjecture in which for general beta, you would expect the same centering, but there will be a sum of a Gumbel and other variable. This is a general feature of logarithmically correlated fields that you expect the maximum is always of the type, the law of the maximum is always of the type of Gumbel plus something else that depends on the details of the model. So that's also what you expect here. And in this context, the result is, the conjecture in the random matrix side is almost true in the sense that except for identifying the second random variable as a Gumbel, the conjecture is true. Namely, the maximum of the log determinant does converge to, after you subtract log n minus 3/4 log n, does converge to some random variable, which is the sum of a Gumbel random variable and something else. That something else for the probabilists is a certain derivative martingale. You can identify it, but I'm not going to discuss that at all. There were earlier and weaker results for beta equal 2 by Argand, Bellius, and Bourgade, and by Paquet and myself. But really the key was an earlier result of Shaibi, Madol, and Najnudel, which actually proved this formula up to tightness. Namely, they proved that the maximum minus this centering, the centering that appears here, the maximum minus that centering, is tight, which means fluctuations of order 1 without proving convergence. And the key part of their proof, they were the first to introduce it in this context, orthogonal polynomials, the determinant of a random matrix of this type can be written as a determinant, which can be written as an orthogonal polynomial with respect to a spectral measure of a particular matrix. And that uses somehow an integrable structure of this joint law of eigenvalues. I should say also that on the Riemann zeta function side, maybe I will write it here, that for the Riemann side, sorry, for the Riemann side, there are now beautiful results of Argand, Bourgade, which again prove so they are the analog of CMN of this result. So they show that you do have tightness of the recentered object. Okay. Now, what am I going to talk about today? So I'm not going to tell you anything about this proof of convergence, both because I talked about it a year ago in Bangalore, and also because that has no dynamics at all. And I thought that maybe I should say something about dynamics in a conference like this one. So what I'm going to talk about is a variant of this problem where the matrices involved are on the real line. I have eigenvalues on the real line. So by this, I mean, first, matrices where the joint distribution of eigenvalues, instead of being on the circle, is now on the line and looks with this form, which I call the V beta E, and for lack of good name, or those are called unitary invariant ensembles. So when V is x squared, this is just a Gaussian model. For beta equal 2, this is just Gaussian random Hermitian Gaussian matrices. By that I mean matrices where the entries above the diagonal are IID and the matrix is Hermitian. For beta, the GOE, the Gaussian orthogonal ensemble. But this makes sense for any beta and for any function V satisfying some gross conditions and a bound from below. So that's the case. So this is one type of random matrices which we want to deal with, G beta E. And the other type of random matrices we want to deal with are so-called Wigner matrices, which are like the GOE or G beta E, except that the entries are not Gaussian. So now we are going to take random entries, IID, but not normal. But they will have variance 1 over n above the diagonal. Okay. Now, for such matrices, the rather well-developed theory of the behavior of eigenvalues, the first fundamental thing is that the empirical measure converges weakly, so in the weak star topology, to a certain law. In the case of the Gaussian case, this limit law is just a semicircle, which is square root 2, square root 2, sorry, minus 2, 2. Apologize. This is minus 2, 2. And the graph here is just a semicircle, square root of 4 minus x squared. And the analogs of what I told you about concerning linear statistics. So I remind you, linear statistic are statistic for the function zf, which is sum of f of lambda I minus the expected value of sum of f of lambda. So everything I told you about the unitary matrices, like the strong sego, etc., there are analogs on the real line. In particular, ZF for F smooth converges in distribution to a Gaussian random variable. There are many ways of proving that, and it's part of the general theory of random matrices. A couple of years ago, the interest started concerning the log determinant. So there is an Eyre-Keating conjecture also for the GUE or for the G beta E. In general, this was put forward by Fyodorov. And a first important step was taken a couple of years ago by Bourgade, Modi, and Payne, where they proved for the V beta E, so not just for the Gaussian set, but for a good collection of unitary invariant models, that the log determinant, properly centered, does converge to a log correlated field. So again, if you integrate again a test function on the real line, it behaves as if you had a log correlated field. Maybe I will say something about the proofs. There's an analog result at about the same time by Augery, Boutez, and myself, where we don't prove the full log correlated structure, but we prove both pointwise bounds for the G beta E, which are using the same type of recursions as in the unitary case. And so the main question that one could ask is, what about the Fyodorov-Eyre-Keating conjecture? Does it hold? What can we say about it? And the situation here is, on the one hand, less satisfactory, we'll see, but on the other hand, it gives us some playground to play. So here is a theorem. This appears in an archive preprint that was posted last month. It's a theorem of Bourgade, Lopatto, and myself. And what it says, the slogan is that the first order term in the Fyodorov-Eyre-Keating conjecture holds. Namely, if you look, so I should say that for general V, if we're talking about V beta E, we are always putting ourselves in a situation, what is called a single cut. So we are taking V's, which are both nice regular, but also that the support of the limiting density of state is a single, is not composed of several intervals, but it's a single, the support is a single interval, and the density does not vanish in the interior of the interval. So in such a situation, the maximum of ln of z divided by ln of z, yes, I have defined. So it's the log determinant of z minus xn minus n times the integral of the log against the limiting measure. So the supremum divided by log n converges to a certain constant that is related to beta. Okay, so if we compare to, let me go back to the Fyodorov to the conjecture. This is like identifying the first order term in this conjecture. Okay. So that's the first result for V beta E.
So for just a second, just to make sure, so the supremum is over Z inside A plus delta B minus delta, not E, right? If I understood. So if you this supremum.
Thank you. It's supremum over Z. So we don't deal. Okay, that's maybe that was not what you intended to ask, but this is what I'm going to answer. That we don't deal with what happens at the edges. Unlike the circular case, the edges are slightly different. One can adapt the conjecture to deal also with the edges, but we don't do that. So we really look at the interior of the strict interior of the limit density of state. Okay? And the supremum is over Z. That was a typo. Now, okay, so those are matrices that have an integrable structure. What about Wigner matrices? So the short answer is the same holds for Wigner matrices, both for beta. And in fact, there is an even stronger result that kind of hints at what we are going to do for the proof. The stronger result is that if your entries of your Wigner matrix can be written as a combination, a convex combination of a Gaussian variable plus something else, where the weight of the Gaussian is of order 1, this is what is called Gaussian divisible, then you actually have a stronger result, both for beta equal 1 and beta equal 2. The difference between the supremum is tight. So we are not giving you the result, the full FHK for GOE, for example, or for GUE, but if you do give me for GOE or GUE, then at least for Gaussian divisible matrices, we can transfer immediately the tightness result to Gaussian divisible ensembles. Okay.
So the assumption on X hat is just it has second moment of the right kind, or there's no further moment assumptions?
No. Okay. So thank you for that. We assume no. So we assume much stronger moment bounds. We assume sub-Gaussian tails, not because it is really needed, but just because the paper is complicated enough as it is, and adding additional truncations, etc., would be.
The universality is supposed to hold only under second moment, or?
So I think that yes, I would say yes, but I don't want to commit myself too strongly. Many elements of the proof would require a serious technical improvement. I will discuss a bit the proof in a few minutes, but all sorts of local laws and local rigidity results, etc., that we use and need are not going to be proved. But they are certainly expected to be true, but they are not proved. The edges are very different, of course, when you don't have a force moment, etc., but we are not near the edges, so that issue is not an issue. Okay? So the related questions that you could ask, which is the following: look at the eigenvalues and look at the typical location of the eigenvalues. This can be measured either as the expectation of lambda I, or if you wish, by the I. So just think of the limiting density and just draw here points such that the total integral here is 1 over n. And up to, if this is the ice point, then the total integral in this region is I over n. So this gives you numbers gamma I, which are the quantiles. So you can ask either what is the maximum of lambda I and the expected value of lambda I, or with gamma I, which is quantile. It's really essentially the same. And this question is very strongly related to fluctuations of the imaginary part of the log determinant. So you could ask, what can we say about such quantity? And the answer is that for Wigner matrices, we can prove that lambda k minus gamma k, if you take the maximum fluctuation, it is of order log n with order 1. So this converges to 1. And in fact, if you take a particular k and you ask what is the distance between lambda k and the quantile, the typical distance is of order square root log n over n with Gaussian tails. And very formally, you see that these two results match each other. If you have independent random variables like that have this kind of tail bounds, they will satisfy this kind of limit. But of course, we don't deal with independent variables, so the proof is slightly more complicated than what I just said. So in particular, we have very strong rigidity result up to the optimal scale on the location of the eigenvalues. I should say that before our work, there were a sequence of improvements on the optimal rigidity. On the seminal work on universality for random matrices, Erdo, Schlein, and Yao, an important step in their proof was to get rigidity up to distance that is mesoscopically larger than 1 over n. And this was improved in series of papers with best improvement up to this work was log n squared over n. Log n over n is really the truth, so it cannot be better than log n over n because maximal spacing is going to be of order log n over n. And this is in the generality of Wigner matrices where you do not have integrability structures. Okay, other questions about COM, because before I tell you something about the proof, or at least I give some sketch of the proof. Okay, so what are the methods? So first of all, you see, there are two types of theorems. There is one theorem about beta ensembles, V beta E, and another one for Wigner matrices. The order of business is to prove results for the V beta E and then transfer them to results for the Wigner matrices. For the V beta E, for the beta ensemble, the starting point is a work I already cited before of Bourgade, Modi, and Payne. The idea was to write down loop equations using the explicit formulas for the empirical Stieltjes transform with good errors. And of course, you cannot directly do it on the real line, but you do it in the upper half place, and you obtain errors which are of this type, 1 over n times the imaginary of z, which means that you can approach the real line almost to distance 1 over n. And in fact, since you need an estimate, since you are after supremums, you want estimates that are uniform, so you need to get a little bit beyond that. And indeed, which is log n to some large constant c over n, you can control these loop equations, and you can control it to the level that you can actually compute exponential moments. So you can compute exponential moments of integrals of these traces, which is exactly integrals in z over a line in the imaginary plane. And once you have such control, once you have such control, you can move to a mesh, and at these points, you can get a control on the exponential moments of the moment generating function of the characteristic polynomial, and therefore obtain by Chebyshev some kind of upper bound on the maximum. But this is not good enough. This is not good enough because while the value, you see, the value of the log characteristic polynomial here is larger than the value here, simply because the distance is larger. So this is an upper bound by itself. That is very good. So I remind you, what is ln of z? Ln of z is just the sum of log of z minus lambda I minus the integral of log of z minus x sigma of dx. So times n. So this part is actually larger here at this point than it is here. Just because you add an imaginary component, you increase the distance. So that goes in the good direction if you want to go do an upper bound. The problem is that when you moved here, this term increased essentially by log n to the power c, which is larger than what we need, because we are after a precision of order log n. So you need to do better, and you need to go down at least to log n over to epsilon log n over n, or preferably to distance 1 over n. And to do that, we use some local law and some you see, we use some local laws that allow you to localize, then you don't need to multiply by n, and then you are in a much better shape. So a very important role in that is played by some a priori overcrowding estimates on eigenvalues. So all that gives you an upper bound. For the lower bound, people who come like me from the extremes of log correlated fields, their first instinct is to do some kind of second moment method, try to analyze probabilities that two separate points are high, have a large value of ln. So what is the probability that ln of z1 and ln of z2 are both high, with certain restriction on how that can happen. In fact, in the first draft, we had more or less a proof written like that. But then we learned of a method that was invented by Lambert, Claes, Fass, and Webb. And it's a beautiful technique, so let me tell you what it is. So the idea is, instead of looking at the original random variable, let's look at the determinant of zi minus xn. So you can see this is, of course, a polynomial. So this is a function on the real line, and it determines a measure simply by multiplication. Or if you take this determinant to power gamma, it will determine a measure on the real line. And if you control well moments of this density, what you can do is you can prove that you converge to a Gaussian multiplicative chaos. which is related to this parameter gamma. So if you look at this determinant to the power gamma, you will converge to a Gaussian multiplicative chaos with parameter gamma. And what CFLW proved is that it's enough to control exponential moments of a suitably smoothed version of the determinant in order to deduce that the GMC, this convergence to the GMC. And once you have convergence to the GMC, it's not very hard to convince yourself that you will get the correct order of the maximum. Why is it the correct order of the maximum? Because points which are not at the proper high value simply are not seen by the limiting measure. And since the GMC gamma is a non-degenerate measure, it means that there must exist points which are at height at least gamma log n. And when you take gamma to the critical value, which is 1 here, you see that you have proved that the supremum has to be at least of order log n. I mean, the supremum over log n is larger than 1 minus epsilon for any epsilon. So that's kind of the proof. It's an idea of these people. And therefore, what you need for that is to have a good convergence of exponential moments. But this is exactly what the Bourgade, Modi, and Payne machinery gives you. So that's the idea. The remark is that this very much simplifies arguments for the law of large numbers, but it only gives leading order, and there is absolutely no hope by these methods to get to second order terms. There's a work in progress with Fanny Augerie, where we are getting the log n correction, but this is not yet ready for public consumption. Okay, so I'm getting close to the end, and I have not yet talked about dynamics. So where do dynamics enter? Well, it's in the universality control. And the idea is as follows. If I have the GOE or the G beta E, there's a motion of the eigenvalues that corresponds to replacing each entry of the GOE by an Ornstein-Uhlenbeck process. If you wish, by a Brownian motion with a drift that causes it to have a Gaussian invariant measure. And the nice thing observed already by Dyson is that when you do that, you can describe the evolution of eigenvalues by themselves as a solution of a certain stochastic differential equations. So the eigenvalues themselves are a Markov chain. You don't need to have, so this is a serious dimension reduction, going from dimension n times n minus 1 over 2 to dimension n, which is a number of eigenvalues. It's not obvious that the projection of a Markov chain is a Markov chain, but here it is. And they satisfy this equation. Now you can start from other initial conditions, same dynamic, but starting from another initial condition. And the nice basic idea of universality or universality proofs goes roughly as follows. On the one hand, we will start our lambdas and our eta from different initial conditions, one corresponding to the Gaussian case, the other corresponding to whatever case you want to analyze. And we will show two things that seem contradictory. On the one hand, we will show that very quickly the distribution is the same. So we will couple these motions and show that the distance between the lambda and the etas become negligible after a very short time. That's on the one hand. On the other hand, we will show that for a longer time, in fact, the distribution doesn't change. And if these two facts are true, which seem completely contradictory, but both happen to be true, then of course it means that when you started, you already had to be close to the equilibrium measure of the Gaussian case, which is what you wanted to show. So this is a device of Erdős, Schlein, and Yao, and in this context of this was perfected in these works of Bourgade, Erdős, Yao, and Yin, and of Bourgade. The point is that you can write now, you see, the Brownian motion enters in both equations in the same way. So if I'm looking at the difference, it's not a stochastic differential equation anymore. It's an ordinary differential equation. You can write it. This is what you obtain when you do that. And now comes this observation of Bourgade that was used by him a few years ago. If you look at this PDE, which has as character, so this is a hyperbolic PDE, and it has as characteristics these curves, which look something like that on the complex plane. And if you take a particular function, what you can show is that what you can show is that the distance between lambda and eta with very high probability follows this function u bar k, which is deterministic. It only depends on, well, almost deterministic. It only depends on the initial condition. Actually, it is deterministic. The randomness is only in the initial condition and in the evolution of the quantiles. So it's a very precise notion of convergence. Now, why is that good? Because, of course, if you evolve it to far enough, you already know that both are Gaussian, so you know that things are close together. So that's kind of the idea. And from that, what you get is that the log determinant at time t, the difference at time t and at time 0, but at a different location, zt, are essentially the same. These are just algebraic manipulations. But now if you take supremum, of course, it doesn't matter that you look over zt or over z. It's essentially the same. So this tells you that you can compare what happens for z minus mu k and z minus lambda k. And the probability for this kind of control is good enough for taking union bounds. So, okay, so now you do the same tricks that I mentioned before. On the one hand, you take t large enough to control, and this will allow you to, if you don't start too close to the real line, it will allow you to push the result all the way there. And then interpolate between close to the real line and the real line, or more precisely 1 over n from the real line, by getting good local estimates and good moment bound with high enough probability and good moment bounds on those local estimates. I should say that the main or the key step is a good a priori moment control on the Stieltjes transform of the difference between the Stieltjes transform and its limit. Okay, attention, and again, sorry I can be there.
Let's thank the speaker. Any questions or comments? I had a quick question. So is there any hope of getting the sort of fractal behavior of thick points moving away a bit from the extreme?
So I think that this one can do directly from the results of
The GMC?
Bourgade, from the GMC, from the convergence to GMC. And Not the convergence itself does not. Okay, you have to define what you mean by the what are exactly the sig points, etc. But and the fractal dimension, because here things are not nested on the same probability space.
Right. Mm-hmm.
Right? When you change n, you change. There is no relation between different n's, so you cannot talk about limb soup or whatever. But if you define,
let's say the metric entropy or something, which is a random
yes,
variable.
exactly. That's what I wanted to say. So if you define properly, then this should come from, if not directly from the convergence, but from the estimates that allow the convergence.
I see.
So in particular, these estimates are strong enough to give you immediately an upper box count.
Uh-huh.
And for the lower bound, the joint exponential moments convergence will allow you to compute a second moment type control on energy. So
I see.
So I believe yes, although I don't think it has been written.
Other questions, comments? If not, let's thank Ofer again.